Have you ever driven past one of those massive cylindrical oil storage tanks and just seen, a big can? Well, today we're going to peel back that steel skin and uncover the absolutely brilliant and frankly life-saving engineering that's hidden in plain sight. And it all starts with what seems like an impossible question. I mean, really think about that for a second. You've got a structure holding millions of gallons of liquid. The pressure down at the bottom is just immense. And you need to cut a hole in it right where that pressure is at its absolute greatest. So how on earth do you do that without the whole thing just failing catastrophically? That right there is the core challenge, and the solution is a total masterclass in mechanical engineering. All right, so let's dig into the problem. We need an access point right at the base of the tank for things like cleaning and maintenance. But cutting a hole in a material that's under stress, it's like making a tiny tear in a stretched rubber band. All that stored energy just wants to rip it wide open. And we're not talking about some small backyard drum here. These tanks can be hundreds of feet across. The liquid inside is pushing outwards, constantly, with this relentless force called hoop stress, and it's trying to tear the steel shell apart. And that force is at its absolute maximum right at the bottom, exactly where we need to make our cut. The stakes, they really couldn't be any higher. And this is the elegant answer. It's called a flush-type clean-out fitting. It doesn't look like a simple door, does it? That's because it's not. It's this complex, prefabricated assembly designed specifically to solve that stretched rubber band problem. This thing is the hero of our story today. So how does it work? Well, the secret, and this is the really cool part, it isn't just about patching the hole. It's about making the area around the hole significantly stronger than the original uncut tank shell ever was. It's a principle that's both super simple and completely ingenious. This is the key concept right here. See, when you cut a hole, the lines of stress that used to flow straight through the steel now have to go around it. And they concentrate dangerously right at the edges of the cut. The whole goal of reinforcement is to give that stress a new, much stronger path to follow. That embroidery hoop analogy is perfect. It grips the fabric all around the weak spot, making sure no single point takes too much strain. Okay, so take a look at this. You can see that principle in action right here. This large, curved piece of steel is the reinforcing plate. Think of it like a massive steel donut that's welded right over the opening. Its entire job is to grab all that diverted stress and just spread it out over a much, much larger area. That prevents any dangerous hotspots from forming right at the cut. But, the forces aren't just pushing on the vertical wall. The engineers also have to think about the connection to the tank floor. And this shows the solution so well. A second plate, the bottom reinforcing plate, gets added to carry that strength all the way down and into the tank's foundation. It creates a completely integrated support system. And get this, look at this detail right here. These pieces aren't just tacked on. They're joined with what are called full penetration welds. This means the weld material goes all the way through the thickness of the steel, literally fusing the plates together so they act as one single solid piece. The way you connect everything is just as critical as the steel itself. Okay, so how do the engineers know how thick to make these plates? I mean, are they just guessing? No way. They follow a very, very precise recipe, a set of formulas that absolutely guarantees safety. All right, now don't freak out when you see this equation. You don't have to solve it. The point here is that every single part of this design is dictated by rigorous mathematics. This formula is the engineer's recipe for strength. It makes sure the reinforcement they add is more than enough to handle all the calculated stresses. And like any good recipe, it's got some key ingredients. H is for the height of the liquid, taller tank, more pressure. G is for the specific gravity, which is basically just how heavy the liquid inside is. SY is how strong the steel itself is. And my personal favorite, CA, is the corrosion allowance. They actually build it thicker than it needs to be today because they're planning for decades of wear and tear. Now that is brilliant foresight. And believe it or not, the precision goes even deeper. Beyond that main formula, engineers use charts just like this one to find special coefficients. These little numbers help fine-tune the calculations based on the exact size and shape of the opening. Every single detail is accounted for, making sure the math perfectly models the real world. So we have the theory, we've got the math, But these tanks, they're built in the real world, on all different kinds of ground, so the design has to be able to adapt. So you might be wondering, does the foundation actually matter? You bet it does. That fitting has to be supported not just by the tank, but by the very ground it rests on. And the API 650 standard actually gives engineers different blueprints for different situations. This is a fantastic comparison. Over on the left, you see a support design for a tank built on a simple dirt foundation. Then on the right, you've got the design for a tank that's sitting on a solid concrete ring wall. See how the support structure underneath is different? The engineering adapts to make sure it has a firm footing, no matter the scenario. And check out this other variation. For some serious extra support, a concrete wall can be built right up against the tank shell. This gives it continuous reinforcement. It's not a one-size-fits-all solution. It's an adaptable toolkit of proven engineering principles. Look, a perfect blueprint is one thing, but turning that design into flawless, high-strength steel, well, that's a whole other ballgame. This final phase is all about quality control. There are 3 absolutely critical steps to get this right. First, the construction has to be perfect. Second, the entire welded assembly is heated to over 600 degrees Celsius in a process called stress relieving that prevents cracking later on. And third, everything, is inspected with a fine-tooth comb. And when I say inspected, I mean it is intense. They don't just look at the welds. They use techniques like magnetic particle examination, which can reveal tiny, invisible surface cracks that could become a huge failure point down the line. Absolutely nothing is left to chance. 100%. That's the key number here. The most critical weld, the one that joins the nozzle neck to the tank shell, undergoes a 100% radiographic examination. That is basically an X-ray for steel, and it guarantees the weld is absolutely perfect all the way through. And then, after all of that, comes the final proof, the ultimate test. After everything's built and inspected, the entire tank is filled to the brim with water for what's called a hydrostatic test. This puts the cleanout fitting and every other part of that tank under real-world pressure to prove without a shadow of a doubt that the design, the math, and the construction were all perfect. So, the next time you see one of these tanks, hopefully you'll see more than just a big can. You'll see a symphony of stress analysis, materials science, and meticulous quality control. Which leaves me with one final question for you. What other invisible engineering is hiding in plain sight, making sure our world runs safely every single day?